probability has its own notation, and how a question is asked can totally change how you calculate the answer. So one thing we need to do when we go through questions with probability is we really need to read carefully. That's a generally good thing to do, but especially with probability, if one little word changes, it can change how you calculate the answer. So what we're going to practice is, first we're going to talk about some definitions that relate to probability, and then we're going to talk about these different rules related to probability that calculate, but we'll really connect with how the question is asked with which rule to use along with it. So let's talk about some definitions. So we're going to have this example where we have these 10 jelly beans. We're going to have 1 blue, 2 purple, 3 green, and 4 red. So we have this set of 10 jelly beans, and we're going to talk about we're drawing 1 jelly bean. So we could talk about is like, what's the probability of getting a purple jelly bean? What's the probability of getting a red jelly bean? What's the probability of drawing multiple jelly beans and seeing something happen? So some terminology here. Experiment is kind of the overall action that we're doing here. So we're trying to produce this random phenomenon. So when I stick my hand in the bag of jelly beans and draw something out, it's random what's going to show up. I have an idea of probabilities of what should happen, but what actually happens is completely random. So in this case, the experiment that we're doing, the actual experiment is drawing 1 jelly bean. So picking a jelly bean out of this bag would be our experiment. Then what we could do is look for an event, which is a collection of these different outcomes that we can see. So typically when we look at probability, we're looking for the probability of a specific event occurring. So I could say, like, an example of an event here would be drawing a blue jelly bean. So that could be an event that I would look for. When we have our events, we'll typically give notation with it. Like if I want to use notation for describing the probability of drawing a blue jelly bean, maybe I'll just talk about using the word blue to represent the probability of drawing 1 blue jelly bean. Or you could shorten it even further. Like I could just use B to represent blue. So I could talk about these events like drawing a blue jelly bean, purple, green, red for short notation, because then it'll be easier if you're working with the mathematical notation. Then our sample space is all of the possible outcomes. So it's kind of like all the possible events even. So like blue was one example, but we could look at drawing a purple jelly bean, a green jelly bean, or a red jelly bean. And with sample space, we use a special set notation, just kind of these curvy brackets around it, to represent sample space. Those are our possible outcomes that we're seeing. When you find the probability of each of these outcomes, if it's the sample space, it should all add up to 1 to represent 100% of the possible outcomes. We wouldn't want to leave anything out. We also wouldn't want to add in more than we actually have. All right, so those are some definitions. Let's talk about notation that we'll see and some ideas connected to probability. So talking about probability, we use this notation where we take capital P and then parentheses, and then we describe our event inside the parentheses. So what I could say for drawing a blue jelly bean, how I would write that is P parentheses B. And that notation would represent, so P always implies probability. So it'd be probability of, and then my event is blue. So it would be probability of drawing a blue jelly bean. So it's a way to write in shortened form probability of a blue jelly bean, just P parentheses with B in the middle. So you'll see this notation show up a lot in this section and just represents a probability of that event that's in the parentheses. In the numerator, we'll take the number of outcomes that fit that event out of the total number of possible outcomes. So for our example, and I'll write it down here with our definition of probability. So probability of an event is a number between 0 and 1. So for this case, if I'm looking for the probability of a blue jelly bean, in the numerator, I want the number of blue jelly beans, which we have 1, out of the total number of jelly beans, which is 10. And then just like we did with proportions, like we start with this fraction, but we'll want a decimal. And when you get this decimal out, be sure to go to 4 places. In this case, it just rounds to a single place because it's a fairly simple number. But if you need to round out further, go to 4 decimal places. And then what we'll do is for our sentence answers, that'll change to a 10%. But really, in terms of a probability, it's all about this decimal coming out. And this decimal should always be between 0 and 1. Every time we calculate a probability, it's like it's stuck between 0% and 100%. So if you're calculating probability and you get a negative number out, that can't happen. If you're calculating probability and you get something over 100% out, that can't happen either. And that's a good tool to use while you're doing these calculations and as we apply these different rules. Keep that in mind because it's a way to double check your answer. Now for formatting here, I want to talk about your MyOpen Math homework a little bit. It comes down to, it depends on how they ask the question. Maybe they'll ask you for the fraction, so you could just type in that as your answer. You could type it in as like 1 divided by 10. If they want the percentage answer, what they'll do is they'll give you the box to type in the number, and what you'll notice is the percentage symbol next to it. So they'll already put the percentage symbol, so you just type in the number. Most often though, MyOpen Math wants the decimal form. I would say most of the time you're plugging in that decimal form, which I know is different than what we're writing. I do want you to write a sentence answer, and you'll typically use the percentage for that sentence answer. But with MyOpen Math and online homework systems, they like to be based on this decimal. Now, for rounding, it's operating to the 4 decimal places. So be sure to be accurate to the 4 decimal places unless it specifies otherwise. They might say round to 3 decimal places, round to 2, and adjust as they ask. But if they don't say anything about formatting with questions on probability, decimal form to 4 decimal places will work with MyOpen Math. All right, let's talk about these 2 concepts, theoretical probability and empirical probability. So let's say we were drawing 10 jelly beans, and I threw in this wording here, and we'll talk about this some more, with replacement, which means when I draw a jelly bean out, I put it back. So with this, it isn't that I'm ending with all jelly beans out of the bag. If I'm putting them back, I still have 10 jelly beans in the bag. It's just I pick one, I look at the color, and then I put it back. And then I pick the next one, look at the color, and put it back. So theoretical probability, so if I talk about probability of drawing a blue jelly bean here, it would be that 10%. It would be that 0.1, because it's based on the construction of our experiment. Meaning how this is designed is we have 1 blue jelly bean out of the 10. So theoretical probability is based on the construction, how it's set up, how you expect things to happen. So that's our expected probabilities. Alternatively, there's empirical probability, where we could set up the same idea of drawing 10 jelly beans and putting them back. And if I wanted to look for the probability of blue jelly bean, this isn't theoretical, it's more what we actually see. So let's say I did this experiment. I got my jelly beans out, I picked 10, and I recorded the color each time I got. So let's say my first jelly bean was purple, then I got a green one, then I got a blue, let's say I got a red, then a blue again. And how many do I have there? 5. Let's say I got purple again, and let's say I got green, and then green. And I need one more, and let's say I got purple again. So this could be something that I actually witnessed, grabbing a jelly bean out, recording the color, putting it back, and I did it 10 times. So my empirical probability would be, out of these 10 times, how many times did I see a blue jelly bean? Well, I saw a blue jelly bean twice. So this 0.2, this 20%, would be my empirical probability. It would be based on what I saw in my experiment. So a way you could think about this is flipping a coin might be something that's more familiar to us. When we flip a coin, I ask you for probability of heads. I say 50%. 50-50, that's how a coin's designed. Half the time you'll see heads, half the time you'll see tails. That would be the theoretical probability. The empirical probability would be if I had you flip a coin a bunch of times, and you could even try this out. If you flip a coin 20 times, it's like you expect to see 50% heads, but when you actually record how many times you see heads out of that 20 times, maybe you'll get 50%, maybe you'll get a little more, maybe you'll get a little less. There's going to be some variability in the values that come out there. So we expect the theoretical probability, but when we run the experiment, the empirical probability is what we get based on our individual data. So let's talk about how these relate to each other as we adjust our sample size. So like I had us choose 10 jelly beans there, but what if I had you actually sample 100 jelly beans, or 1,000, or 100,000? What if I had you perform an empirical probability with very large sample sizes? Because what we saw is, like, in this case, only sampling 10, there was a big difference in the probability of blue jelly beans. But as we repeat the process more, it's going to get closer and closer to that theoretical probability. So like in terms of flipping a coin, you flip a coin 20 times, maybe you'll see 70% heads. But if you continued flipping the coin like 1,000 times, that proportion of heads is going to get closer and closer to 50%. So it happens, this long run empirical probability, that's relating to as your sample size gets larger. So as you repeat the process more and more, that empirical probability that you're looking at based on your experiment is going to get closer and closer to the theoretical probability. So that's where it's going to get closer to the true theoretical frequency or theoretical probability that we would expect to be happening. So with small sample sizes, you can see a lot of variability, like theoretical and empirical probabilities could look completely different. But as you take larger sample sizes, that empirical probability should kind of converge to that theoretical. So that's our law of large numbers. And that's why sample sizes, the larger the sample size, the more accurate the data is. We really want to avoid small sample sizes because there's a lot of variability there. All right, two last little pieces here. You're going to see this wording for disjoint show up, and we'll talk about this more in the next videos too. Disjoint, or you might see mutually exclusive, those are interchangeable, they mean the same thing. This is when two events cannot occur at the same time. So for example, if I'm drawing a jelly bean and I want this probability that it is blue and purple, that's not possible here. This case of drawing jelly beans, they're disjoint because if I look for this probability of being blue and purple, it would just be 0 because there aren't any jelly beans that are both blue and purple. We have blue or we have purple, but we don't have both. So that would be that they're disjoint, they're separate from each other. If you're used to seeing Venn diagrams, if they're disjoint, this would be the case where the probabilities are separate from each other, they don't overlap. If they're not disjoint, then what you would have for a Venn diagram is you'd have that space of overlap there. So another piece that we'll talk about is independence. This is typically for a sequence of events. So if I want to see certain outcomes occurring in a row, independence is when if one event has occurred, it doesn't change the probability of the next event. So like say I'm flipping a coin and I want to see, I'm going to flip a coin twice and I want to see heads and then tails. So probability of heads, 50%. When I go to my next event and think about what's the probability of tails, knowing that I already flipped heads, Well, the coin hasn't changed. It's still 50-50. So probability of tails is still 50%. It doesn't matter that I flipped heads before it. It's still a 50% chance. So that would be independent. The idea that each time you flip a coin, it doesn't matter what previous results you got. When you go to flip that coin the next time, it's still 50-50. Same thing with rolling a die. With this jelly bean case, which we'll come back to, it depends. It depends on whether or not we're replacing the jelly beans or not. If we're working with replacement and just putting them back, then the bag of jelly beans hasn't changed and all the probabilities are the same. But if we're taking out jelly beans and working without replacement, so not putting them back, like say I draw a jelly bean and then I eat it and it's gone, all of the probabilities in the bag changed. And then we would have something that's dependent. So we'll talk about those concepts more in the next videos.